Finally, you have a process in the process of quality control. You can look at one little part of this report and just see current risk is acceptable, potential risk is not acceptable. And you can see the numbers behind that. This is the premise that the QC sample was tested to represent patient samples with a true value of 100 units. Our medical staff and scientific recommendations concur that results between 80 and 120 are relevant, accurate, and reliable for patient care. Current risk is acceptable, potential risk is not. What are the financial implications? The estimated current cost is $0, but if 5% of results after this failure fail, you don't know how many are going to fail after a hazardous event occurs or after a failure occurs. But if it was 5%, then 415 fewer patients would receive medically unreliable results, saving $20,793 in clinical or legal costs from incorrect or delayed treatment. Where did that come from? It came from your estimate of the average cost of a medically unreliable result. And that is a difficult number to set. We've sort of set it normally at about $50, but the cost of a glucose that fails the 10% limit is very different than an HIV that is reported as a false negative. There's much to be done yet with this process. But you can calculate, based on the numbers you put in, what are the clinical implications, what are the financial implications. So you start, is risk acceptable to the risk manager? And you can see here, no, it's not. They've graded this as a risk-based grade C. Does it meet the goals? It passes. Current risk is acceptable. You're costing nothing in lab errors right now. Your potential risk fails with the existing QCP, can pass if you mathematically optimize it. It is not acceptable, and if you mathematically optimize QC, if the method fails, you would save $1,300. And you can see what it looks like, and you can see that the existing QC process is going to take 2 runs to detect the error, where the mathematically optimized will only take 1.